The dawn of quantum theory, Einstein, photons, and the strange nature of light. In the early 1900s, the world of physics was poised for a revolution. Classical physics, built on Newton's laws, seemed solid and unshakable. Yet, as scientists probed deeper into the mysteries of light and matter, cracks began to appear in this seemingly perfect system. One of the key figures in this transformation was a young and relatively unknown physicist working in a Swiss patent office, Albert Einstein. And the strange idea he proposed would eventually change how we understand the universe. The photoelectric effect, light as particles. In 1905, Einstein published a groundbreaking paper where he made a bold claim. Light wasn't just a continuous wave, as most scientists believed. It also behaved like particles. He called these particles quanta. The idea was shocking. At that time, the wave theory of light, championed by James Clerk Maxwell, had been incredibly successful in explaining phenomena like interference and diffraction. But Einstein noticed that certain experimental results, particularly the photoelectric effect, didn't fit the wave theory. The photoelectric effect involves shining light onto a metal surface and observing electrons being ejected. Strangely, it wasn't the intensity of the light that mattered, but the frequency. Low-frequency light, no matter how bright, couldn't dislodge electrons, while high-frequency light, even dim, could. Einstein's solution: light must come in discrete packets of energy, or quanta, with the energy of each packet proportional to its frequency. E equals hf, where h is Planck's constant. These quanta would later be called photons, a name coined by Gilbert N. Lewis in 1926. At first, the scientific community was skeptical. Even giants like Max Planck and Niels Bohr rejected Einstein's particle theory of light. For nearly 15 years, his idea sat in the shadow of doubt. It wasn't until 1919 that Robert Millikan's precise experiments with the photoelectric effect provided convincing evidence that Einstein was right. With the discovery of Compton scattering, where X-rays scattered off electrons like billiard balls, the particle nature of light became undeniable. What Einstein had proposed in 1905 was finally accepted. Light could behave both as a particle and as a wave. The implications were profound, but this was only the beginning. Quantized atomic vibrations, the Einstein solid. While Einstein's work on light quanta was still controversial, he continued to explore other areas where classical physics was falling short. One of these was the mystery of heat in solids. In 1907, Einstein proposed a model that would offer a quantum solution. He suggested that atoms in a solid lattice weren't free to move as they pleased, but rather they oscillated like tiny, independent harmonic oscillators. The catch: their energy was also quantized. This meant that the atoms could only exist in specific energy states, separated by fixed amounts, rather than having any arbitrary amount of energy. This model, known as the Einstein solid, was revolutionary because it helped explain a long-standing problem in classical physics: the specific heat of materials. Classical theory couldn't explain why the heat capacity of solids drops sharply at lower temperatures. Einstein's quantum approach, though imperfect, showed that quantum mechanics had the potential to solve these mysteries. His work was later refined by Peter Debye, who made it fit experimental data even more accurately, especially at very low temperatures. Bose-Einstein statistics, the birth of a new state of matter. In 1924, Einstein's work took another leap forward, this time thanks to the Indian physicist Satyendra Nath Bose. Bose had developed a new statistical model that treated light particles as indistinguishable entities, effectively treating light as a gas of particles. He sent his ideas to Einstein, who immediately recognized their importance. Einstein expanded Bose's model beyond just light, applying it to atoms. He predicted that if you cooled a gas of certain atoms, now called bosons, to near absolute zero, they would collapse into a single quantum state, forming what would later be known as a Bose-Einstein condensate (BEC). It wasn't just a theoretical curiosity. This new state of matter was a dramatic display of quantum mechanics on a macroscopic scale. For decades, this remained a theory. It wasn't until 1995 that Eric Cornell and Carl Wieman, using ultracooling techniques at the University of Colorado, successfully created the first Bose-Einstein condensate. For the first time, Einstein's nearly 70-year-old prediction came to life in a lab. Wave-particle duality, bridging two worlds. Even as Einstein delved deeper into quantum theory, he continued to wrestle with the dual nature of light. Was it a particle, a wave, or something in between? In a 1909 paper, he explored how light might behave as both. He showed that Max Planck's energy quanta just also have well-defined momentum, meaning that in some respects, light behaved like point-like particles. This concept, wave-particle duality, would become a cornerstone of quantum mechanics. It meant that light and later, all particles could act as both waves and particles, depending on how they were observed. This strange duality opened the door to a new world of physics, where the boundaries between particles and waves blurred, and the certainty of classical physics gave way to probabilities and uncertainties. Stimulated emission, laying the foundation for lasers. In 1917, during his work on relativity, Einstein stumbled upon another breakthrough, one that would later revolutionize modern technology. He proposed the concept of stimulated emission, where an incoming photon could cause an excited atom to release another photon in sync with it. This process, he suggested, would result in a cascade of identical photons, all traveling in the same direction. Though purely theoretical at the time, Einstein's idea laid the groundwork for the development of lasers, light amplification by stimulated emission of radiation, and masers. It wasn't until the 1950s that this concept was put into practice, but once it was, it transformed fields ranging from telecommunications to medicine. The matter-wave revolution, Einstein and de Broglie. As quantum theory advanced, Einstein played a crucial role in supporting young physicists with new ideas. In the 1920s, French physicist Louis de Broglie proposed that particles, such as electrons, also had wave-like properties. This idea initially faced skepticism, but Einstein recognized its brilliance. De Broglie's theory suggested that particles could have wavelengths associated with them, and this could explain the quantized orbits of electrons in atoms, as proposed by Niels Bohr. Inspired by de Broglie's work, physicist Erwin Schrödinger developed his famous wave equation in 1926, one of the foundational equations of quantum mechanics. This confirmed the existence of matter waves, the idea that particles can behave as waves under certain conditions. A legacy of quantum discovery, the early development of quantum theory, driven by Einstein and his contemporaries, was marked by dramatic shifts in how we view the universe. Concepts like photons, wave-particle duality, and Bose-Einstein condensation were born in this period, reshaping not just physics, but our understanding of reality itself. Einstein's relentless curiosity and willingness to challenge established norms propelled him into the forefront of the quantum revolution, even as he later wrestled with some of its stranger consequences. The seeds Einstein planted in the early 20th century grew into one of the most successful scientific frameworks we have today, quantum mechanics, a field that continues to astonish and challenge our perception of the world.